Swayam Prabha. Digital India. Educated India.
Thank you. You probably did not hear what I'm going to speak about. I'm sorry I could not share the title with Dinesh earlier. It's just been a hectic couple of weeks. I'm a cosmologist. Can you comment about what cosmology implies, what cosmology means, what cosmology deals with? One at a time, one at a time. That is not on? Okay. Someone else? Okay. We'll hear other views. Study of the? Cosmos. Absolutely. So the point is, we are not interested in astronomy, which is anything outside the Earth. Okay. It of course, and the universe encompasses the Earth as well. We are not interested in cosmic rays. That is one aspect. And what was the other answer? The different states of the universe. To some extent, it is true. We are interested in the physics of the universe as a whole, and that's what cosmology is. Do you know what is the current model of cosmology? Do you know the name of the current model of cosmology? There is something said cyclic cosmology, Big Bang cosmology. Anything else? May not be. I'll clarify. Yeah. Any other comments? Any other suggestions? I'm asking, what is the current model of cosmology referred to? It has a popular name. It has a more standard name, and it has a popular name. I would like to know whether you know the popular name. Technically it is referred to just like you have a standard model of particle physics. I'm sure, I would imagine someone have talked about the standard model of particle physics. There is a standard model of cosmology, but there is a very popular name. Someone mentioned it. There is even a famous American sitcom. It's called The Big Bang Theory. And my goal in today's talk is to explain to you, within the limited time available, why we believe that the universe is described by the hot Big Bang model. You should understand that virtually every civilization historically has its own model of cosmology. But something drastically has changed over the last 100 years or so. We have taken great strides in the field of observational astronomy, which has led to this, discovery first of the expanding universe. Something I will refer to as the cosmic microwave background, something that is referred to as the cosmic microwave background. You would have heard about the fact that the universe is accelerating and therefore it is dominated by dark energy. And there are CMB, what are known as cosmic microwave background. I will refer to it repeatedly as the CMB. Please keep this in mind. There are what are known as anisotropies in the CMB, which are being measured with greater and greater precision. All these observations has led to this, what is known as the standard model of cosmology, and it is, in the popular parlance, it is referred to as the hot Big Bang model. What I want to emphasize is that in contrast to what happened before 100 years or so, we have a scientific model of cosmology which is driven by astronomical and cosmological data. That's what I would like to I would like to tell you the story of why we believe in the hot Big Bang model over the next couple of hours. You're welcome to stop me and ask questions. If I have a simple answer, I will provide that then. Else, we'll wait towards the end of the talk for me to answer in some more detail. In order to, I'll just come to you in a minute, okay? Before we proceed, we need to know what the universe contains. So I will start with a survey of the universe, but there is a question even before that. Please go ahead.
Sir, can you just repeat the difference between astronomy and cosmology?
So astronomy is, there was suggestions that we are studying cosmic rays, and there were suggestions that we are studying something just beyond the earth. Astronomy is observing anything which is celestial, beyond earth, as was suggested. Okay? When I say cosmology, I'm interested in the physics of the universe as a whole. I am not interested in the physics of some stars here, some galaxies here, or even collections of galaxies. We are interested in the physics of the universe as a whole. In order to know what does the universe contain, I will have to start with a survey of what the universe has. I will do that. Okay? In summary, astronomy is just observing the universe. Okay? In contrast to other aspects of physics, I can't carry out experiments with my world, with my universe. I have to observe it. I observe. That is astronomical. There is a subtle difference between astronomical and cosmological data. When you try to understand the behavior of a star here, a galaxy here, you have astronomical observations. But there are certain observations which tell you about the universe as a whole. Then you refer to them as cosmological observation or cosmological data. And similarly, if you are trying to understand the physics of a star, physics of a galaxy, you are interested in what is known as astrophysics. Okay? And the physics of the universe as a whole is what we refer to as cosmology. Is that clear now? Sorry? I need to know how the universe, what does the universe contain, how it came into be, how is it evolving. No, we have to look at all places. What I am trying to say is that if you look at this particular corner of the sky, all right, and understand the behavior of stars or galaxies, that doesn't tell me about the complete universe. Okay? It will become, maybe you need to be a little patient, it will become clear after a few slides what I mean as the physics of the universe as a whole. Okay? As I mentioned, what we need to know is what the universe contains. Since many of you may not know what all the universe contains, okay? Whatever we have observed, that is what I mean. I will start with a survey of the universe. What we will do is that as we see around, you see a star here, you see we are part of a galaxy, which I'm sure you've heard of. And there are many, many galaxies, and there are clusters of galaxies. And in fact, there is a hierarchy of structures that we talk about. We are part of a solar system. We are on a planet. The planet is part of the solar system. The solar system is part of the galaxy. And I will tell you the galaxy is part of some small group of galaxies. And that in turn is formed part of a cluster of galaxies. And there are clusters and clusters of galaxies. And these whole thing forms our universe. Okay? And evidently, when I say structure, when I mean structure, I'm talking about structures on large scales. I will explain what that large scale is. This is the division between astronomy/astrophysics and cosmology. Okay? What is the scale at which you are observing? Evidently, if you are focusing on the dynamics of the Earth, it's not cosmology. Or even if you focus on the dynamics of a galaxy, it's not cosmology. You are interested in truly large scales, and I will try to explain what that large scale is. So the structures, you would have seen something known as the distribution of large-scale structure. I will show some pictures of it as we proceed so that you can have a picture in your mind. To understand our universe, there is no smoothness. There is galaxies and clusters of galaxies. But in order to simplify, mathematically describe our universe, it happens to be simple to assume that there is a smooth universe. I will explain what is smoothness. We assume that is a smooth universe, on top of which there are small deviations. Think of a plane, and there is a smooth distribution of matter, density in the universe. Okay? And something did induced some changes, and it started, the smoothness got disturbed. And when the smoothness gets disturbed, gravity plays a role. Gravity is always present. And what will gravity do when there is smoothness that has been disturbed? It will start, gathering matter. And that's how structures are supposed to have formed. So the first part of the story is about, which I will try to cover in the next 40-50 minutes, is to understand the composition. What does the universe contain? And how did it evolve? What is this Big Bang that we are talking about? Why do we believe there was a Big Bang? And then we see this hot Big Bang model is not very good. It has its problems. I will try to explain in the second lecture what are the problems. All right? And I told you that we are going to assume that the universe is smooth. And I will give you reasons to believe, observational reasons, okay, to believe that very early in the universe, it was indeed smooth. That is, the energy density was smoothly distributed. But it's not today, right? You have a galaxy here, you have a galaxy here, a cluster of galaxies. There is empty space in between, all right? How did this? So the challenge is to understand why is the universe so smooth on one hand. At the same time, how did these structures, these galaxies and clusters of galaxies form? There is an idea called the inflationary scenario that is introduced to induce these deviations from smoothness, which grow, as I mentioned, due to gravitational instability. Gravitational instability implies, just that if you have a smooth distribution of matter in this room, and the moment I add a little mass here, it's smooth initially. The moment I add a little mass here, what will happen? Due to Newtonian gravity, all the other mass will start getting attracted towards this large mass. That's what gravitational instability is. So if I have smooth distribution of matter, the moment something causes some fluctuations, right, it will induce what is known as gravitational instability. And that is why these galaxies and clusters of galaxies that are supposed to have been formed. So I will explain what are known as perturbation. Do you understand the concept of a perturbation? When, I am perturbed, what does that mean? Sorry? You are disturbed, that's right. You are gently disturbed, not greatly disturbed. A perturbation in physics means something which is a small disturbance. You may have thought of the simple harmonic oscillator, right? X cube potential, right? X squared, potential, right? It is described. If I add a small plus alpha x cube, where alpha in some units is a very small number, then you call it as a perturbation. So what we will see is that there were very tiny perturbations in the early universe, okay? And then due to the gravitational instability, which I have repeatedly mentioned to you about, okay, it grows into the structures that we see around us today. And all this leads to the standard model of cosmology. The cosmologists don't refer to it as the Big Bang model. It is, it is in the popular parlance. In fact, the name was given in a derogatory sense. I will comment about it much later, okay? And what we refer to it as the standard model of cosmology, and close with some, useful references for you to read. I should mention, there are aspects of this story which will be difficult for me to convey. You need two things, to understand cosmology completely. You need to know something called theory of fields, theory of electromagnetic fields, and there are other fields as well. And you need to know what is known as the relativistic theory of gravitation, which is general relativity. In order to appreciate cosmology completely, you need to know this. To derive all the expressions I may have, I have tried to limit the number of equations I have on the slides, okay? You will need that theory in order to appreciate it completely, but if you are curious, you can speak to me. I can refer you to some textbooks where you can broadly understand how these equations arise. Let's proceed. So we start with a survey of the universe. Where do we begin? We begin with our galaxy. This is a picture of our galaxy taken from outside the galaxy. Do you believe that? Why? We have hardly gone beyond Voyager, I believe, is one of the earliest satellites sent into outer space. and it has hardly gone beyond the end of the solar system. So this is a picture taken by the Cosmic Background Explorer, COBE. We will encounter this satellite later. Okay, it is a picture of our galaxy. What it did was that it had an infrared camera, and it just exposed the infrared camera to all regions of the sky. And it arrived at this picture. So what do you see? You see a flat pancake or a dosa, but it's not quite a dosa, but it has a bulge in the middle. So it becomes a appam, right? It's not a dosa. It has a bulge in the middle. In fact, what you have is what is known as a spiral galaxy. We are not able to see the spiral arms because we are in one of the arms of the galaxies. We are in a plane of the appam, and therefore we are not able to see. And there are a few things which I want you to learn about this. We are not so much worried about the galaxy. Very soon, you will recognize we are not only Earth, not only the solar system, even our galaxy is some tiny irrelevant speck in the whole universe. Okay, so we are not interested in our galaxy as such, but it is just to help you understand some numbers. The size of the galaxy, the diameter approximately of this disk is about 45,000 light years, or we will talk about a strange unit called a parsec. It's about a 3.26 light years, and I explain why this number comes about, and what it is about 15 kiloparsec. You typically say that the size of the galaxy is 15 kiloparsec. You don't need to write this down. I can make these slides available somewhere. You can download and look at it whenever you want. And there are some useful links as well, which you can peruse. Okay. So what do you have? One of the things I want you to appreciate is that it contains about 10 power 11 stars such as the sun, right? This object you see here, M with a circle and a dot in the middle, is the mass of the sun. The mass of the sun is about 2 times 10 power 30 kilograms. So what you see is that it doesn't work here. Okay, it is about 2 times 10 power 12 solar mass. Notice what you have. It has about 10 power 11 stars, but its mass is about 10 or about 20 times larger than all the stars put together. Can you guess what it implies? No, that's not what it implies. Yeah, there is some other strange matter present in the universe, okay, present in the galaxies. We will come to that. There is matter other than matter which shines like the stars, and we will talk about it as we proceed. And what is this? Why are we talking about this 3.26 light years? I'll come to you in a minute, okay? Let me just explain this idea of a parsec, which is 3.26 light years, okay? So what you do is as follows. I presume you know the idea of trigonometric parallax. It's a simple idea. So this is the average radius of the Earth around the sun. It's referred to as 1 astronomical unit. You look at a star 6 months apart, say in July and January, and you take a picture of the star, which is a nearby star with respect to farther away stars. Okay, so this angle is some P, and this distance is D, and using basic trigonometry, and if you measure this angle, right, you can measure the distance to the star. And you can do a simple algebra, okay, and what you find is that, if P is 1 second of arc, what is P? It is this angle here. The angle subtended by the star 6 months apart with respect to farther away stars is 1 second of arc. Then you can show using basic trigonometry that it corresponds to about 3.26 light years, and I assume you know what a light year is. It's the distance traveled by light in a year. So it is because of this strange, distance, namely the astronomical unit, that is the radius of the Earth's orbit around the sun, we have this unit of 3.26 light years, and we will talk in terms of kiloparsec. 1 parsec is about 3.26 light years. We will talk in terms of kiloparsec, and very soon in terms of megaparsec. Okay, so we go beyond our galaxy now, and I can quickly address the questions that were asked. Yeah. Very good question. We'll come to that. Okay. I will not be able to, I need to complete the story. Okay. So I have enough slides. So I may not be able to answer everything in this, within this 2 hours. I'll be glad to be available during coffee break or lunch break so that I can answer additional questions. You had a question. So you can measure using something known as rotation curves of galaxies. Okay. There is one slide which we come to it. In fact, that is what it tells us about using Newtonian physics and rotation curves of galaxies. Okay, galaxies rotate, and you can look at the rotation curves. Okay, what it means is that you can look at the spectrum of stars, look at their Doppler effect, measure their velocities, and using Newtonian physics, you can estimate what is the mass of the galaxy. Yes.
Sir, in the calculation which you did for the for showing that the mass of the galaxy has other stuff which is not accounted for by the stars, the sun is a very small star comparatively. So, like,
sorry.
The sun is a smaller star.
No, we are talking about yes. I said it contains about 10 power 11 stars. We didn't, such as the sun. So you typically say that, I am not saying all stars are like the sun. There are about 10 power 11 stars. On the average, they have the mass of the sun, but the mass of the galaxy is more than that. Okay? All right. So let me proceed with the story. Okay? What do we have? We are going beyond our galaxy. And as I mentioned, there is a hierarchy of clusters in the universe, hierarchy of structures in the universe. As you look around, there are many other galaxies, and we form a part of something known as a local group of galaxies of about 30 galaxies or so. The galaxy on the left is the Andromeda galaxy. It's called M31. If you have seen through a telescope, you may have seen that as a blurry object in the sky, provided you go far away from Chennai. Okay? And there are other galaxies. This is called the Triangulum galaxy or M33 galaxy. Remember this M33. I talked about rotation curves of galaxies. You had some questions. There is a slide much later, where we come back to this galaxy. And notice what is the distance to the Andromeda galaxy. The nearest galaxy, we actually have very tiny satellite galaxies, circling the Milky Way, all right? But if you look at the nearest largest galaxy, that happens to be the Andromeda galaxy, and look at the distance to the galaxy. It's about 700 kiloparsec or so.